Hello, and welcome to our next on-air EMEA Demo Derby session. If, like us in the developer relations team, you are hands-on and you like to see things for yourselves, then you've come to the right place. My name is Alexi, and I am joined today by Anu. Good morning, Anu.
Good morning, Alexi. Today, in the next 2 hours or so, we're going to share with you over a dozen exciting new demos made by our Google Cloud DevRel team. So we have demos on machine learning, then we have a section on infrastructure and operations, and last but not least, app development. So we're going to see some exciting things all on recent announcements at Cloud Next on Air. Today we have this broken off into 3 different sections. So we're going to start with ML and big data. After that, we'll move on to infrastructure and ops, then app dev.
And each of these sections will have 4 or 5 demos, and they will be followed by a live Q&A with the demoers. If you scroll down on the Next on Air video page, you'll be able to submit your questions. So as questions come up, simply type them in, and we'll do our best to get to them all at the end of each of these sections. We will also provide written answers to these questions.
So now, without further ado, let's dive into the first section, machine learning and big data. So in our very first demo, Kaz will show you how to use Cloud Vision, AutoML tables, text-to-speech, and Cloud Functions to solve his problem of having too many books to read. Over to you, Kaz.
Hi everyone, I'm Kaz Sato, developer advocate from Google Cloud. In this video, I'd like to introduce a tool called PDF to Audiobook. What is PDF to Audiobook? The problem was that I had too many unread PDF books. I have scanned almost all the paper books into PDF, but I didn't have no time to read them all. So the solution is to build a tool that converts the PDF books into audiobooks so that I could spend my jogging time, exercising times for listening to the audiobooks. Let's take a look at how it works. You can upload the PDF file onto your Google Cloud storage so that it could be automatically converted into multiple MP3 files. And you can download those MP3 files and listen to the audiobook. How it works. I have used Cloud Functions to write a short Python code that combines the multiple APIs from Cloud AI. This is a function as a service to run your code with zero server management. So the use case like this, like a writing demonstration or POC code, the Cloud Functions works best for you. This is the first function I've written for the Cloud Functions. This function will be triggered whenever you are uploading the new PDF file on a Google Cloud Storage bucket, so that it will try to get a bucket object and file name for that, and then pass the bucket and file blob to the next PDF OCR phase. And also, I have used this command, gcloud functions deploy command, for registering this function as a Cloud Functions. After the first function is triggered by the Cloud Functions, the whole phase of the processes will be started. The first, it will start the OCR with Vision API, and then it will start using the AutoML tables for the feature extraction and layout classification. Lastly, it will use the text-to-speech API for speech synthesis. Let's take a look at how the OCR with Vision API works. Vision API is the machine learning API with the pre-trained API. So you don't have to have the machine learning expertise to use that. All you have to do is to just upload the image data to the API so that you'll be getting the result within a couple of seconds. In this case, I have used the OCR feature or text detection feature of the API. So like the screen you are seeing now, you'll be able to get the multiple paragraphs detected in a single PDF page. But there are some unnecessary parts you want to remove from the audiobook. For example, the page headers would include the numbers of the labels on each page repeatedly, or that you don't want to listen to the diagram labels, small captions, and also you may want to remove those page numbers. So to remove those unnecessary or garbage text, I have used the AutoML tables for the layout classifications. What is AutoML tables? AutoML tables allows you to build your custom machine learning model for the tabular data, such as the Google Sheets or Excel spreadsheet or the tables in the databases. It does the defining the schema and data types of each features, and it automatically analyzes your input features, and also it tries to automate a major part of the training, like feature engineering or the model selection and hyperparameter tuning. In these demonstrations, I have used the features like this. So these are the features you got from the OCR result. I have used the text of each paragraph, and I also used the number of the characters or the width and height of each paragraph. That gives you an area of the paragraph. That means you can also get the character size of each character. And also you can also use the features like position, X position, Y position of each paragraph, and aspect, layout, and so on. So I have put all of those features into the AutoML tables to train a model that predicts the target label, whether each paragraph should be on body text or header or maybe caption label or the other garbage text. Let's take a look at how the AutoML table works. So at first, you can define a data set and create a data set by uploading some CSV file or specifying some files on the Google Cloud Storage or tables on BigQuery. So you can easily upload the training data set. Once you have created the data set, it will show the detected features in each data. So it tries to detect the data types of each column, like a numeric or categorical or string and so on. So you can check, and if needed, you can correct that. And also you can specify the what column or what features you want to use for training the model, and start training the model. That would usually take like 4 to 6 hours. Then you'll be getting the result like this one. So this is the evaluation result of the trained model with the AutoML tables. As you can see, my model was able to get the 95% precision rate and 94% recall rate, which is not so bad. So I thought this could be useful for building the tool. And also with the report, you can also get the other information like confusion matrix, where you can take a look at how the prediction for each labels would perform. For example, for detecting body text, the model works at 95% accuracy. And for removing the garbage text, it works at 97% accuracy. Also, the report includes the feature importance. With that, you can learn what are the important features the model is using. In this case, the model is using the text itself as the most important features, because the AutoML tables has the natural language processing features inside it. So it tries to understand the difference between each paragraph, whether this paragraph contains multiple natural languages with multiple sentences, or this paragraph only contains like a numerical symbols or just URLs and so on. Lastly, I have used the text-to-speech API to synthesize the speech. Again, this is another pre-trained model-based the speech synthesis API. So you don't have to have any expertise on using this. All you have to do is to call the REST API and pass the text string to the API. So you'll be getting the generated audio. In these demonstrations, I have added some SSML tags for the speech synthesis, so that the speech synthesis tries to add short breaks between the paragraph, or having more breaks between the captions and headers. Lastly, I have used the Google Apps script to build the annotation tool. Because it took so long time for me to prepare for the training data, so I have used the Google Sheet for preparing the training data like this one. So for each paragraph you are seeing on the sheet, you have to manually put the labels on there, whether it's some body text, it's a header of the section, or it's on the caption of the label and or the other garbage text and so on. And it took like 2 or 3 hours per book. Instead, I have spent some time on building an annotation tool with Google Apps Script. So the annotation tool shows each paragraph as the rectangle with color. So each color represents the label of the paragraph, whether it's a body text or the section header or caption diagram caption, or maybe other garbage text. And it uses the pre-trained model with the AutoML tables. So in early phases of the annotation process, it provides it makes many mistakes. So by looking at those colors, the human operators can easily update the labels. So if you keep using this annotation tool and keep training the model again and again, you'll be getting the much higher accuracy. The end result is 10 times higher productivity. Now I'm able to annotate on a single book within 15 minutes compared to the 2 or 3 hours per book. If you are interested in those products, please take a look at the product pages of these products. And also, you can find my sample code on this repository. Thank you so much.
Thank you so much, Kaz. We'll see you in a bit for the Q&A session. Just a reminder, if you just scroll down, you can leave us any questions that you want us to answer.
Next up is Laurent, telling us all about his use of AutoML Vision to solve a very specific problem he has had with circuit boards. Here's Laurent.
Hello, everyone. I'm Laurent. I'm speaking from Paris, and I'd like to show you how you can solve unique problems with AutoML. So let's imagine your company or our company is producing electronic boards like this one, printed circuit boards, PCBs in short. And we'd like to set up a production line where we will recycle the boards. We would like to reuse these components. So for instance, we would like to auto-detect them and auto-extract them. This is a very hard problem. Before we start, we should check out the state of the art. So there are vision models, right? Already, the Vision API. If we give it a PCB picture, then we will get lots of insights from this picture. So we get labels. It tells us, okay, this picture is about a motherboard with very high confidence, and that's great. This is a motherboard. There are electronic components. This is great. But if I want to be more precise and look for objects, that I will get only one object. It will tell me that, yeah, there's this object on this picture. But I want to be more precise. I want to detect objects. So I have a unique problem to solve. And AutoML is here to help. So to use AutoML, first of all, we need a data set. We need to create a data set like this and to specify which kind of problem we want to solve. We don't want to recognize or classify pictures. What we want is detect objects. This is an object detection problem. Okay, you do that. You have your data set, and once it is ready, you can start importing pictures. Either you have two choices. Either you import pictures from your computer directly, or you do that, and this is what I've done with a CSV file. So my picture, I have put my pictures in a cloud bucket, and in the CSV file, what I do is I just specify the location of all my pictures. Then I continue and import the pictures. Okay. When it's ready, I can see my pictures. And then what I need to do is specify the bounding boxes of all the components. So this is the tedious part. The data set, the model will be as rich as your data set is, right? Don't forget one, otherwise your model won't be as good. And once you've done that, then you can launch the training, okay? you train a new model like this, you have two options. Either you want the state-of-the-art model and you can choose a cloud-hosted model. It will create a model, a big one, that will be hosted in the cloud, on Google Cloud, and it will serve you your own private API. You can also choose to train an edge model, and in this case, your model will be lighter and you'll be able to export it to get it to run elsewhere. We will see that a bit later. You have, again, different choices. Maybe you want to favor fast predictions, but in our case, we want high accuracy. We want to be able to detect components precisely and with the highest accuracy. And then you just need to specify your budget. How long do you want to spend for your training? I typically start with just 1 hour for an edge model because I make mistakes. Typically at the beginning when I have a data set, I make mistakes. I am a human. So after 1 hour training, I can realize how my model is doing and maybe iterate one or twice on my data set to improve it and to fix the mistakes I've done. Once I'm ready or once I'm confident, then I can launch a training with a higher budget. The cool thing is that AutoML will stop automatically on its own when the training has converged, when the model is not getting any better with more hours. Okay, so this is actually saving training money. Once it's done, then you receive an email and you can evaluate your model. So here I have a cloud and an edge model. Let's see the evaluation. One thing interesting to know is that within the samples that you've used for the model, 10% of them are used at the beginning to evaluate the best neural network architecture. Then a training is launched with 80% of the samples. And finally, the last 10% are used to test your model, to know exactly how well it's doing, how it's comparing to what you expect. Okay, and per component, here I just have one, but you can here have a detailed evaluation of what it's finding, what it's not finding on a case-by-case basis. And then you can move on. You can ask to deploy your model. I have my model, my cloud model is deployed here, and then you can test it with any picture, and especially pictures it has never seen. So here I am uploading 3 pictures from my test set, so it has not been trained on it, otherwise I would be cheating. And then it's able to give us predictions and auto-detect the components. Here it does detect all of them, the 22, here the 19, and here 20 objects. But the fun thing is that in my data set, I forgot this component. And so it appears as a false positive, but this is actually a true positive. So here the model is beating me, doing better than what I did. Okay, so this is also a way to iterate and improve your model when you realize you've made mistakes. So now I can use actually this model in production if my factory has connectivity. But let's say we don't have connectivity, or for some reasons we cannot access the API. This is where the edge model is handy. So it's a lighter model, and you can export it, this one, to get it to run wherever you want. You can get it to run in a Docker container. You can get it to run in a mobile app with a TF Lite export, TensorFlow Lite. But you can also do a TensorFlow JS export, and in this case it will run in a web page. So this is what I've done to show you my test demo. So here is my desktop. I am simulating the production line, And this is the webcam. It is a really nice webcam that is able to do a really nice autofocus. And now I'm moving to the tab where I'm going to start webcam acquisition. And here you see my pen, you see my little buddy. Okay. And now let's try an actual PCB. And as you can see, it is running offline in a web page, and it is able to find my components. I have solved my unique problem thanks to AutoML. Now I'm ready. I can go to the production line and I will deal with calibration, and especially I will need to control my lighting environment because I want everything to be steady to get always the same level of predictions. But I've solved my problem. Great. Before we end, I would like to thank Martin Campbell, who is the original author of the PCB dataset. I just used over 100 pictures from this dataset. As you could see, we managed to solve our problem thanks to AutoML Vision, but it also works on videos, on text, and on data. So it's up to your imagination. I hope it gave you a few ideas. Thank you, AutoML, and I hope it will help you to solve your own problems. Thank you all very much. Bye-bye.
Well, thanks, Laurent. I love to see how you solved that particular problem you had with the model running actually in a browser. This is amazing. See you in a bit for the Q&A session.
Next up, we have Mark, who will walk us through Cloud AI Platform Notebooks. This is Google's version of Jupyter Notebooks, and he's going to show us these great, awesome advanced features. Take it away, Mark.
Thanks, Anu. I really love talking about Jupyter Notebooks because they hit this sweet spot with both the commercial market and the educational domain. We're training students to use a tool that they can then apply those skills in their future careers. For those of you who aren't familiar with Jupyter, I thought I would give you a quick background on it. There's bunch of words here, but I think the most effective way to show what it's all about would be with a quick demo. So it's basically an interactive document that contains both text and code. For example, I can open this markdown cell and I can change the text, and it'll actually change that link content interactively. And then in addition to explanatory text, I can have interactive code, which I can run. So this is running a graph of 2 dimensions, horsepower and miles per gallon for vehicles from 3 different regions, color-coded by the region. The other really cool thing about these notebooks is you can change the code. So for example, I'm going to have this method called .interactive to the code I just ran, and I'll rerun it, and it becomes an interactive chart. So that's really nice. These are great for learning, teaching, but also in industry, they're great for capturing processes. They've become particularly popular for machine learning and data science applications. So with that as background, there are a couple of different options to use Jupyter, but the one I want to focus on for today is called AI Platform Notebooks. And again, these are, I'm gonna give you a demo to explain what they're all about, but these are really intended to be high performance notebooks for production use. So let me jump into the Cloud Console and we can see what the interface looks like. This is a project where I've set up a couple of AI platform notebooks. If you're looking for how to navigate to this page, you'll go to the usual navigation page and choose AI platform, and you'll get a bunch of capabilities that are unified for AI applications. And I'm going into the notebooks page here. What you'll see is that I've created a couple of notebooks already, but just to give you a sense of the process for creating these notebooks, you'll be able to click on New Instance, and you'll choose a notebook type, which, for example, I'll just pick TensorFlow Enterprise 2.3. That's the notebook version I've been playing with the most lately. I'll say without GPUs, and then I get a bunch of options to customize. I can name my instance, of course. I can specify a region and a zone. Under advanced options, I get to configure the underlying details of the hardware configuration, which is really valuable. I can also tweak the environment for different pre-canned setups of notebook arrangements. I can change the operating system. But here's the really cool thing. I can choose any of the supported hardware configurations by Google that are currently supported by Google Compute Engine. And I can select a GPU type. I can configure the disk, the networking, the whole thing. So I'm going to click Create. And that will take a little while. It takes a couple minutes to configure everything and provision it. But I've got a couple pre-built notebooks, and I'll show you what it looks like to actually use these. So once they're done being set up for you, I've got one for Python and one for R. You click this Open JupyterLab link, and it takes you to a JupyterLab environment. Now, JupyterLab is an open source, kind of like an IDE, an integrated development environment specifically for working with Jupyter Notebooks. So I've got some predefined notebook in here, a predefined notebook in here I call Demo, and I can click Run to run this cell. And it's really just importing some stuff. But the next cell is doing something interesting. It's using Google BigQuery right from within this notebook. And so I've defined a query in a triple quoted Python string, and I'll just run that, and taking the output of that query, converting it to a pandas data frame, and displaying the top 5 elements in that data frame. That all looks good. Next, I'll do some data cleansing. This is just filling in the NA values and cleaning up the data a little bit. And then finally, I'll train a model using that updated cleaned data. So this is doing a Keras, very simple Keras model on this data, and it's obviously going really fast because it's not demanding too much in the way of computing resources. The next cell is actually going to do some predictions, and I'm going to uncomment it. It's not really a comment, it's a triple quoted string, but effectively functions like a comment. I'm going to uncomment it and run it, and I'll explain why I uncommented it in a second. So that just ran, gave me a bunch of predicted values and actual values. I'm getting a little bit of feedback. I could have graphed that if I wanted more visual insight. But what I wanted to show you is I'm going to save the notebook, and now I can go to the GitHub page. And what you're seeing is the integration of GitHub right into the notebook environment, right? So this is really powerful because it introduces the idea of being able to treat these notebooks like source code, where you can check them into GitHub, you can diff them, and so on. So here's and that's why I uncommented that. I wanted to make some change to the notebook source so I could show you how this works. And you see here, this is the file I changed. This is the notebook where I just made that small modification. And I can click diff, and it shows me a nice side-by-side color-coded diff. One of the changed outputs is the values I got from one of the cells. And so you can see that the scope of source control is both the code cells, the text cells, but also the output from the code cells. The other change here is the output from the training session, which obviously is slightly different than the previous go-round. Same with my predictions. And then, yeah, so this is the cell where I uncommented it, commented the code, and you can see that it's now showing as a change. So what I can do is say, let's stage this change, and let's give it some sort of, I'm not going to be very creative right now. I'm just going to say commit message. We'll say commit that change to my repo. It's committing it. And then I can click this upload to the cloud item, or I can use the git push to remote. Either one will do the same thing. But this is now pushing the change to the GitHub repo where this originated, and now that's done. So now if I were to go to my GitHub repo online, or if you were to clone my repo, you would see the changed version of the notebook. I'll show you one other example. And by the way, my previous notebook is now up and ready to go, and I can start using this or share it with my team. I'll just show you an R notebook, and this is one of my favorite things because R has become just a really popular, for quite a while now, language with particular strength in statistical analysis and also in data visualization. So now I'm using my R notebook. I get a notebook I've pre-set up with some R code just to show off some nice graphical things. But Yeah, so this is how you can use R inside a notebook and harness all of that power. So to jump back to the slides, I did want to call your attention to this manifesto. So this is a nice blog article where the creators, some of the lead creators of Google AI Platform Notebooks have kind of enunciated the principles, the thinking behind this particular kind of notebook. There are a lot of different ways to run notebooks in the cloud. But this one in particular I like because it takes care of a lot of the administrative burden you would have if you wanted to build your own infrastructure. And it's really built to make it sort of engineering centric. So if you're using notebooks in a corporate environment, a production environment where you want all the best practices of traditional software, modern software engineering principles, that's kind of what went into the design of these notebooks. Final note is these slides you're seeing come from another talk that I gave that's more comprehensive. I'm kind of giving you a snapshot of just the Cloud AI Notebooks piece. There are two other notebooks to know about. There's something called Colab, which has become quite popular. Many of you may have already used that, but that's a very simple notebook model. You don't get the JupyterLab IDE. You just kind of end up right in a single notebook, but it's very convenient, very low bar to entry. It's free, and it's built on kind of a Google Docs model. There's also Kaggle notebooks, which are very tightly integrated into a community of machine learning practitioners and data scientists. So that's a great option if you really want to go deep in the data science area. Not only do you have the capabilities that are also managed for you and integrated well with the cloud, but you will also find lots to learn because you can go and see which notebooks were used to win certain competitions, and just there's a wealth of learning material there. So to summarize, Colab is great for casual use, teaching and learning environments. Kaggle is for deep dives into advanced data science and machine learning. And the notebooks that I demonstrated for you today, the AI platform notebooks, are really intended for industrial professional use, where you want to incorporate the best engineering practices, and also where you want predictable performance, where you can specify the hardware and make sure it's available in full for your notebook application whenever you need it. Finally, there's a very nice automation AI, notebook automation AI, available with AI platform notebooks, which gives you the ability to programmatically control your notebooks. This talk is available if you want to read more at the URL down in the lower left here, mco.fyi/nb. And I hope you enjoyed the demo this morning. Thank you for your attention.
Thank you so much, Mark. That was great. We'll chat with you again in just about 15 minutes for the Q&A. So just again, a reminder, please send us your Q&A questions by scrolling down.
Thanks.
So now we have Camus showing us how simple it is to build a machine learning model with BigQuery ML and deploy it to Cloud AI Platform for predictions, all starting with the popular census dataset. Over to you, Camus.
Hi, my name is Camus, and I'm a machine learning specialist based in Google Paris. And today I'll be showing you how to build a model in BigQuery ML and export it to AI Platform for prediction. So let's get started. Over here we have the training data set. So this is the famous census data set, and it has all the information about individuals in the United States, including whether or not they make over or less than 50K a year, which is shown here by the income bracket. 0 means they make less, and 1 means they make more. So let's go directly inside our Jupyter Notebook. Over here, I have two notebooks. The first one is to show you how to make a deep neural network model and then export it as a TensorFlow model to AI Platform. This is a basic select statement. Because this is an AI Platform notebook, all I have to do is set it up, and without any additional configuration, I have access to data in BigQuery, Google Cloud Storage, for data that's already in the same project, which is super nice for getting started. So this is a simple SQL query, nothing fancy here. And over here, this is the query to build the actual model. So as you can see, it's nothing fancy as well. You have your simple create or replace model, you give the model a name, and you specify the type of model. And then the rest is the same. You have additional hyperparameters that you can set, but you can leave it blank and it'll take defaults, and the query will still work. So I pre-executed this before the recording, so we can have a quick look of how this looks like directly in the UI. Right here, you have information about the training. And also you have some evaluation metrics of the model itself. We can also see this inside Jupyter Notebooks. Here you have some training info. So you have how much was lost in each iteration, you have the learning rate, and the duration of each iteration as well, which is nice. You can also query for metrics about the model itself, such as the accuracy, the recall, the precision, or other information that you might need. Next, we'll export the model to Google Cloud Storage, where then we could tell AI Platform to make a prediction based on the model that's located in Google Cloud Storage. We could do so using the CLI, or we could do so directly in the UI itself, which I will show you now. So say I have this model right here. We click Export Model, we browse in Google Cloud Storage, and then we choose a folder. So I exported this beforehand, and then we can see all the information about the model, and it's a TensorFlow model with some checkpoints. Cool. So now the model is in BigQuery. As proof, we can list it right here. And now we will make the model in AI Platform and then make a prediction. So the model there is the bucket, which I just exported to. And then we'll specify a model name, the version, and some additional information about the model. And then using the CLI, I could create the model. And then using CLI again, I could create a version. Again, we could do this directly in the UI, or we could use the CLI. This is some information about the model. That we could see in the CLI as well, UI as well, sorry. So let's see how this looks like inside the UI. Over here we have our deep neural network census model and the version. And then in the version, we can see the exact same information that I saw in my notebook. And now let's make a prediction. Right here I have the test.json file. And it's just an example. So the age, work class, something we want to make a prediction on, whether or not the income is greater or less than 50K a year. So right here, we can make the inference. So there you go. As you can see, we build a model in BigQML, we export the AI prediction, AI Platform prediction, and then we can make an inference. Similarly, we could do the same thing for XGBoost. The only difference is that we change the model type to XGBoost, and the hyperparameters might change as well, but as you can see, I specified none here, so it will take the defaults. Thank you very much for dialing in, and I hope you learned something today about BigQuery ML and AI Platform.
Thank you, Camus. This was great. We'll see you in a bit for the Q&A chat if you're available. And with that.
Yeah, now I am really excited to introduce my colleague and actually my neighbor, Zach, who will tell you about how he used AutoML to train a model and deploy it to the edge to automate classification of landfill garbage. The floor is all yours, Zach.
Thanks, Anu. Yes, I am going to be presenting a bit of a unique demo that I've built that utilizes AutoML object detection, similar to that Laurent presented a wee bit earlier, but this one has a bit of a twist on it. So let's get started. What I'm going to do now is I'm going to put on a VR headset because I've actually built this demo inside a virtual factory. So I'm going to put this on. I'm just going to make sure, yep, that's all coming through. Cool. So this is live VR. Nothing can go wrong. All right. So what we have here is we have a virtual factory. And the name of this virtual factory, I call it HindCycle. And HindCycle's job, their mission statement, is to dig up all of the landfill and recycle it properly. Because apparently, in hindsight, that wasn't a good idea. So I've got here the factory floor as it stands now. And we're going to have, here we go. So here's the first bit of rubbish coming through now. I've got to sort this. So I pick it up and I put it into the organic bin and I get 1 point for that. Excellent. Oh, we have more fish. And we keep going. Cool. Keep going up. Excellent. So it looks like the factory runs smoothly. Oh, I missed one and I went down one. Oh, and now we're starting to scale up. So we've got a bit of a scaling issue. Oh no, this isn't going to go well. Okay, this goes into the plastic. Okay, yeah. Okay, so we've got a scaling issue in our factory. And I think it's obvious that some kind of machine learning might be helpful here. To get started with that, we probably need to collect some images. And so we're going to need a camera. So here is our camera. This is capturing just kind of this area of the conveyor belt. And you can probably see as I hold this, this is going to be taking images. Cool. You can imagine this will be like the eyes of our robot that we want to then like detect what happens and then grab it and then put it in the right bin. So that seems like the kind of solution we want to build. So right now, what we're doing is we're using this camera to collect just images that we're then going to use to feed into a machine learning model that's then going to predict stuff. So this is at the moment just collecting, we call them unlabeled images, so images with effectively no kind of information about what's in them yet. And we're going to take these unlabeled images and we're going to feed them into AutoML. So let's do that now. I'm going to recenter myself, coming over here. So I've got a laptop. I'm going to start this, hopefully be still inside of the microphone. So we've got here the AutoML UI, and I've uploaded my unlabeled images, and I've actually used the AutoML UI to draw boxes around the things I wanted to detect. So I've went around about 100 or so images and said I wanted to detect these different categories, which are like plastic, recycling, organics, all that kind of stuff. And then I can go and click the training model. I can see that I've got enough labels for each one. And very specific to my factory, I want to train it for the edge because I want our model to run actually in the factory floor and run with nice low latency. So I say, okay, train a model that's going to be reasonably accurate and reasonably low latency, and then click train. And now AutoML is going to go off and do all the training in the cloud. And after an hour or two, I'm going to get an email and I'm going to be allowed to download the model locally. And here it is. So here is the model. It allows you to download a TensorFlow Lite model, which is a standardized format for deploying machine learning to local devices. So pretty much anywhere you can run code, you can probably run a TensorFlow Lite model. And luckily, in our factory, we are running code. So I'm going to come back over here. I'm going to plug it in. And away it goes. So it's now, for each image that it was just taking and doing nothing with, it's now taking those images and running them through the machine learning model that we trained in AutoML. And when it finds an object, it moves the robot hand to pick it up and deposit it in the right bin. And as we scale up, we should see, because it's a local model, it's going to run with nice low latency and still be able to keep up with the problem at hand. And a point to note, this demo, although it's a virtual factory, it's like a game and such, this is actually running the TensorFlow Lite model that I trained in AutoML, and it's actually all running on the device that I'm using, which is an Oculus Quest, and under the hood, it's just an Android phone. So it goes to show that if you want to do the powerful training in the cloud, you can do that. And then if you want to deploy it locally, even to run on the phones with low latency, you could totally do that with AutoML and GCP. So yeah, it looks like we're going to reduce the deficit of landfill, and we're going to be using TensorFlow Lite to do it. So that's my demo, and thank you very much.
Thank you, Zach. That was amazing. Very eco-friendly. Now it's time to, we'll be back with our Q&A starting very soon. So it's now time for our first Q&A session with some of our presenters. So here we will be asking questions to Zach, Mark, Kaz, and Laurent.
Welcome, everybody. A reminder that you can ask questions at any time by just scrolling down. We'll try to get to most of these. Let's get started with our first question. The question is as follows. Do the ML language APIs like text-to-speech work in other languages? And I believe that question is most likely for Kaz.
Yes, the text-to-speech supports for how many was that? I checked it. But I think it's supposed to 40 different languages with 200 different dialects. And you can easily try that out on the product page. So you please go to the text-to-speech product page on the cloud.google.com.
That's
Okay,
great.
wonderful.
So our next question. So we saw a lot about AutoML. So well, we'll start with Zach. What's the best way to get started? How do you decide which problems are good for ML? And do you have any recommendations for managing costs with AutoML?
Oh, yes, excellent questions. Best way to get started is just to, I would recommend going to the Google Cloud Docs, because there we've got kind of quick examples of like, here's like data sets. Like one of them is like detecting like fruit for production and stuff. So I recommend just looking at, seeing examples, seeing what other people are doing with ML. Another good option is, well, there's a website called Kaggle, which is like data scientists repository of all these different projects and data sets. And just like scrolling through there, seeing what other people are doing, kind of gives you a feel for what people are using machine learning for now and kind of what it can be used for and stuff. So yeah, I recommend looking at Kaggle. Regarding costs around AutoML, I recommend there's three main considerations. Is like, do you need your model to be hosted in the cloud? Do you need real-time predictions in the cloud? Or can you, are you okay with maybe like, you just need to make a lot of predictions at once, and then you don't mind if you wait a couple of minutes to get those predictions, because we've got hosting your AutoML, deploying it for live serving, or batch predictions. So I recommend just investigating the difference between batch predictions and hosted models, and seeing if the latency and the cost matches up with your use cases. So yeah, those are the main considerations: hosted versus batch.
Excellent. So here's another question. Can you talk more about the pros and cons of notebooks? You showed BigQuery and touch on visualization. What other products do they integrate with? And that, I believe, is for Mark.
Yeah, so because notebooks provide a programming interface, you can access from a notebook pretty much any service in the Google Cloud you would like using one of the supported client libraries now. Some notebooks are limited in terms of the languages they support. For example, I showed R and Python. Those are typically the most commonly used programming languages in notebooks. But if we talk about Jupyter in general, there's actually a ton of kernels available to support lots of different languages. But to come back to the cloud integration question, depending on which client library you're using, and most likely it's Python for one of the three types of notebooks I talked about, you have access to all of the cloud services you can use with the Python API, which is quite extensive.
Great, interesting. Yeah. Next question. Okay, so this is on edge computing. So how small should models be to be deployed on the edge? I guess that's also for Zach.
Depends how much memory you have on the edge. What's nice about, I think, the AutoML export to edge feature is I believe all the models are around the same size, which is around 5 or 6 megabytes. So things like Raspberry Pis and mobile devices, that's not a big deal for. Things like Arduino is like really low level embedded software, which only has like kilobytes of memory, then that's a bigger consideration. So yeah, depending on the hardware you have to deploy it on, will restrict the size. But yeah, usually 5 or 6 megabytes will deploy to most places.
Great. And that is actually a great segue into another question, which I believe is for probably Laurent, but both of you are touching on fairly similar things. So, how much time did the models need for training? Specifically, Laurent, in that case, we'll start with you.
Yeah, hi. Zach, you will maybe complement me, but in my case, I'm seeing always the same patterns. I'm pretty stressed because I want the best quality model, right? So when I'm satisfied with the data set, very often I choose to launch a 12-hour or 24-hour training. It's not necessary. And in my demo, so for the PCB IC detection, my cloud model, I gave it 24 hour of budget, but actually it finished it converged and ended the training in less than 2 hours. So there are different reasons. So first, a cloud model, the training is distributed. So it was actually trained on 9 different nodes. So this is why it's, by experience, it's going about eight times faster. And so in less than 2 hours, I had an excellent, almost perfect model. In the case of the edge model, so I think for timing, it's not distributed, but my model converged in less than 5 hours. So usually data scientists, they launch the training in the evening and they come back the next day, or they wait for a couple of days. But here we are talking about a matter of a few hours. So that's great. Zach, do you have anything?
Yeah, that pretty much mirrors my experience the same. Like I will, for the model I trained here, because it was kind of like a very kind of sterile environment where it's a game and all the lighting and stuff is very, very static. My model, I gave it like a couple of hours to train and it converged in like less than 2 hours. And with other projects, like I've done other projects with actual like real world images of like sport and stuff, and it's the same story. I'll give it 10 hours of budget and it will converge in like 2 or 3.
Wow.
Great. I think that's all the questions we've had for this section. I want to thank all the presenters here. And with that, thank you very much. We'll be right back. Don't go away for the next section, which is infrastructure and operations.
So it's now time to move on to our next section of Next on Air EMEA Demo Derby. Get ready for infrastructure and operations.
And to kick things off, we have Simon walking us through Cloud Operations Sandbox, a demo app provisioned with everything you need to learn SRE or site reliability practices with logging, traces, profiling, snapshot debugging, SLO monitoring, alerts, and more. So here's Simon.
Hello, and welcome to the demo of Cloud Operations Sandbox. Cloud Operations Sandbox is the learning experience that allows you to learn how to use Cloud Operations suite of tools and apply the practices of SRE into your production workloads without actually risking those production workloads. This tool was born as a result of the feedback that we received from many customers saying that they want to evaluate how to use different tools from Google Cloud on environment which is production-like, but at the same time isolated from their existing production workloads. And so we created this experience where you can just go and click on the Open in Cloud Shell button at cloudopssandbox.dev, and then a couple of things will happen. So let's talk about that. First of all, you will get a demo application that will be provisioned in a click of a button in a one-click deployment script. That application is the microservices demo, which is written in multiple programming languages using the cloud native stack. And it kind of illustrates what the modern system might look like. You also get the synthetic load generator, which is the tool that allows to send synthetic traffic into your demo app, and with that you can simulate what would happen with the real traffic coming from different geolocations into your application. And then we also provide SRE recipes, which is the new gamified experience where you can break the cluster, manufacture errors without knowing what those errors are, of course, and then try to figure out what is the problem using a cloud operations set of tools, and then verify the hypothesis that you probably came up to using the tools that we provide. And of course, all of that is supplied with interactive walkthroughs and additional guides that allow you to go through this in a comfortable way. Okay, so let's get started. I'm going to cloudops-sandbox.dev, and then all I need, this is the landing page. It's really short and concise. You just click on a button here, open in Google Cloud Shell, and then the Cloud Shell window will open with a machine that will clone the code from our public GitHub repository, and it will start the deployment of the cluster. Now, the deployment itself may take a while. It probably takes about 20 minutes or so to deploy, so we won't really do the entire deployment. We'll just start with it, and then we'll talk about what you get and explore the existing application that I created for these purposes. Okay, so first of all, we need to choose the billing account so that we can associate the billing account with the project that is going to be created with the demo app. And you can also see that on the right-hand side, alongside the script that's running here, we also get a bunch of nodes that help us understand actually what is going on, what is going to happen step by step, what should I expect. I can go back and forth and learn about the experience of deploying the cluster, and then obviously there are next steps that we'll see shortly. So kind of getting back to the script, I just click on create a new sandbox. And the creation is just getting started here. As I said, it will take some time, so we won't waste all of this time, but I'll show you what happens as this gets finished. So first of all, you get this demo application. This is the architecture of this app. A bunch of microservices talking to each other, e-commerce shop with external components and upstream dependencies. You have the synthetic load generator that is sending traffic from a different geolocation so that the latencies are real. And when this deployment is finished, you will get a screen that looks like this. And in the screen, you have a bunch of URLs. Each URL is useful for different purposes. So let's talk through this. First URL is the Kubernetes dashboard, and that dashboard allows you to see the list of all the microservices that were deployed into GKE. Then you have this project URL, so all of the different components of cloud operations are going to be available in this project, and we'll go there shortly and see what we get out of the box. Then we have this demo application URL and the load generation URL. So let's see the demo application that was already pre-provisioned. So this is the e-commerce shop, multiple products that you can buy, add to carts, and then change currencies and do a bunch of other things. And then if you want to send the synthetic traffic into this, one of the links that were provided at the end of the installation was the link to our load generation, which is looking like this. So let's start load generation. Actually, when you just deploy the cluster, the load is started automatically, but you can, of course, stop and change it. So let's do 20 users with a spawn rate of 2, start swarming. And what is happening right now is that this Locust framework that allows to send queries into the cluster is sending requests into multiple endpoints of our demo application. And it tries to simulate a specific traffic pattern that we discussed. There are multiple patterns that we support here. I'll not go into details because of the shortage of the demo. But you can see that there are some graphs that show what is actually happening right now. You can also see failures if they exist, exceptions, and so on. So we just send the traffic, and let's explore other pieces of this demo. So now that we send the traffic, it means that some signals should be generated, and we can see the signals using different products that are part of the cloud operations. So first of all is cloud monitoring. With cloud monitoring, one of the things that you get out of the box is custom dashboards. So I'm already in the custom dashboards view, and you can see a bunch of dashboards here. For every microservice, you get a custom dashboard that was pre-created using Terraform. So it's created in a declarative way. If you want to see how we did that, so you can apply it into your existing services, you can go into GitHub of our product, so cloudops-sandbox.dev, and then just go into view source, and you will get access to all of that, and you can try it out. So going back into our custom dashboard. So in the custom dashboard, we get a bunch of charts which are pre-created, and these charts show different signals that SREs like to look into to understand better different dimensions of the service operation. So you can see we have CPU limit utilization, we have request count, we have error rate, and a bunch of other stuff. And this is for every single microservice, and it's all pre-created. Second thing that we get is the service monitoring. So with service monitoring, we pre-provisioned custom service definitions. So let's explore it just on the email service, for example. So you can see here that we have a custom service definition that has some alerting policies and service level objectives defined. So you can see here, the first one actually shows that it's very unhealthy. It exceeds error budget by like a lot. And you can see here, this is the line of the error budget. This is the actual availability of our system. And it's graphically easy to see that something is not working here. And we can delve into this and understand better what's going on. And this information is available in the timeline, and it's kind of broken down by different microservices. And it's all coming kind of out of the box. We also have alerting policies predefined for all the microservices. So if you exceed the error budget, if the alerting rule triggers, you will get an email to the account with which you created this demo experience. In addition to that, we instrumented all of these microservices with OpenTelemetry, and that allows us to see the operation of different microservices, which microservice calls which. So this is the graph of all different trace activities. I can just click on the specific one that I want to explore and see the entire chain of events, which service called which service, how long it took, and I can see the entire chain of events this way using OpenTelemetry. And this instrumentation exists in 4 programming languages, so you can use it as an example for your own purposes as well. With Profile, we also get additional instrumentation that allows us to understand within the scope of a particular method that is running in one of the microservices, what are the bottlenecks, what are the methods in code that might take longer than they should. So this is the flame chart. In this case, we show the product catalog service, but there are others that are also instrumented with profiling, so you can explore others and see what's going on with their activities as well. With error reporting, you also get the aggregation of all the errors that happen in the system as a result of the synthetic traffic coming. And for every for every error, you can also see the number of occurrences for that error. And if you go into deeper details, you can also see the call stack and associate this with the logs for that microservice. So a lot of the information is already pre-created and gathered in a way that should be useful for you to understand better what the system does and how it performs. And even more so, if you just get started with cloud operations and you just want to kind of have the walkthrough of all the available tools and what's the purpose of each tool, we also have this additional comprehensive guide in here. So if you click, you will see a guide that has a lot of screenshots that briefly explain what every component of the system can do for you, why is it used, and how you can apply it into your scenarios and find it useful. So to sum things up, with Cloud Operations Sandbox, you can create a learning experience in a click of a button. It's way more comprehensive than just doing the code lab. Sometimes people try to create an environment for the code lab and might get stuck just in that piece. And here you get a smooth experience where in a click of a button, you get something that gets you up to speed really quickly with cloud operations. And you can also replicate that onto your environment by just going into our GitHub and seeing how we implemented all of that. All right, so with that, I want to thank you for the attention and I hope to see you among the users of the Sandbox. Thank you very much.
Thanks, Simon, for the really comprehensive tour of cloud operations using the Sandbox app, demo app. Unfortunately, Simon is unable to join us for the upcoming Q&A session, but be sure to ask your question nonetheless at the bottom of this page, and we'll make sure to provide you with an answer written.
So it is now time to tackle the #1 most discussed issue for serverless apps, cold starts. Who likes waiting? So in this next demo, Valentin will walk us through using Cloud Run with their new min instance feature, which can help you avoid cold starts altogether.
Hi, my name is Valentin Deleplace. I'm a developer advocate for Google Cloud. Today, I'd like to show you an exciting new setting in Cloud Run, which lets you specify a minimum number of instances running at any given time. I love the serverless computing model mainly for 3 reasons. First, because the infrastructure is managed by the cloud vendor, which means that I don't have to worry about operating system security patches, for example. Second, because it can scale up very high and very fast. Third, because it can even scale down to 0, which means that I'm not paying anything when the service is deployed but not in use. To achieve all of this, the trade-off is that I can't control every aspect of the underlying hardware, and I'm not in charge at all of starting and stopping instances. A major side effect of this model is that when my app has 0 running instances, then the next incoming request will experience a high latency because a new instance will need to be booted and initialized before the request can be processed. This is what we call a cold start. On the left, a normal request is processed by an existing compute instance. On the right, a loading request triggers the creation of a new instance. Its response time is much higher because of infrastructure provisioning and application initialization. The user is experiencing a cold start, which is not a pleasant experience because it's very slow. Cold starts are no big deal when the app latency is non-critical, when it affects only a tiny percentage of the request in the total volume of traffic, or when starting an instance is extremely fast. This depends a lot on the specific details of the application. For some apps, it makes perfect sense to not scale to 0 at all, in order to dramatically reduce the frequency of cold starts. For example, when an app is often idle, but the latency is critical to the user experience. This is now possible in Cloud Run with the min instances setting. I built a demo app which consistently takes 5 seconds to initialize and 1 second to process one request. The code in Go is pretty straightforward. Let me show you. So 5 seconds here to initialize and 1 second to process one request. Okay. So a normal request is expected to take a little more than 1 second, taking into account the network round trip, and the loading request is expected to take more than 6 seconds, taking into account the time it takes to boot a new container instance before the app can initialize itself. This is how we specify the new setting when deploying in command line. Min instances equals 1. And the setting is also available in the Cloud Console when you deploy a service. So let me show you in my project. I have a service min1, and if I check the specifics of the revision, I will see on the right, autoscaling min instances set to 1. Okay. And if I decide to deploy a new revision, then I will be able to specify a new minimum number of instances. So I have two URLs, h0 for the default settings, which are equivalent to min instances equals 0, and h1 for min instances equals to 1. Let's see if we can stumble on a cold start. So time curl to, I will send a request to h0. The service is called. I expect a total time around 7 seconds. Let's see. Yes, almost 7 seconds for the first request to h0, and the subsequent request should be much faster because the service is warm, so it's very fast now, only 1 second. I will send the same kind of request to the service h1, which has the setting min instances set to 1, and also which has not been used recently. So let's see if we experience a cold start. No, that's cool. Cold start will be extremely rare in those under normal usage in those conditions. We always have at least one instance running. So deploying a service to Cloud Run is pretty fast, so I suggest we do it live. I have it in my clipboard. So deploy min1, and it says error, the min instances flag is not supported by the GA release track. Indeed, I need to specify gcloud beta because it's a beta setting so far. Okay, it usually takes less than 1 minute. We'll come back to it. I made a benchmark for a fictional low traffic of only 60 requests over a period of 14 hours. That's around 4 requests per hour, but not uniformly distributed. As you can see, the new setting has solved the infamous cold start problem in this contrived example, because instead of 31 cold start, we experience exactly 0 cold start with the new setting. This is what the latencies look like when plotted against time. Oh, yes, as I mentioned, deploying takes only 30 seconds, so it's pretty fast. Cool. So having 50% of the requests trigger a cold start is not a good user experience. Having 0 cold start, thanks to the new setting, on the other hand, in this specific example, is a much better experience. And although it does cost more to keep warm instances running continuously, it turns out that idle instance CPU time is much cheaper than active CPU time. So the total cost is still very acceptable in the end. Well, that's it for today.
Wow, that was incredible, Valentin. Thank you so much. I've been using functions for years, so I'm really excited to start using Cloud Run and boost my deploy and start time.
Hey, but Valentin, since we have you here, you could probably tell us all also about Cloud Run's graceful instance termination feature and how that can be leveraged by developers to persist any transient in-memory state when required. So back to you.
Hello again. I'll take a few minutes to explain the concept of graceful instance termination in the context of Cloud Run. As some of you may know, this is a fancy term for handling the sick-term signal. So, what is this all really about? In App Engine, Cloud Functions, and Cloud Run, we insist that the application must be written in a stateless way. Basically, this means that the code of the application is allowed to perform computations and to communicate with stateful services, but it is not allowed to hold any persistent data. This is directly related to the autoscaling nature of Google's serverless products. The service automatically scales up horizontally when the user traffic grows by starting more instances to handle more concurrent requests. And likewise, it automatically scales down when the traffic decreases by shutting down some of the instances. By default, it can even scale to 0 when in instances. From a logical point of view, the service is equivalent to one single compute unit, which processes all the requests independently from each other. It doesn't matter how many instances or virtual CPUs are actually used. It also doesn't matter when an instance is killed, and as there is no loss of data, precisely because the victim is stateless. In an ideal world, a Cloud Run instance doesn't hold any persistent data, and the developer never really cares about anything bad happening when an instance is shut down. This is true for the majority of serverless applications. However, there are a few corner cases where instances are not 100% stateless or need to actively clean up their cloud footprint. These bits of clandestine state are usually related to optimizations of latency or runtime, memory, network payload, or money. Here is an example where a Cloud Run application is contractually mandated to inform a third-party external web service for each occurrence of a specific user action. The external service is a sink in the sense that it's not used to produce the end-user HTTP response. However, Cloud Run makes an external request to this service with some metadata for each user request, with no exception. It turns out that the external service is a paid service, and it's not exactly cheap. Every single call is billed 1 cent, 1 euro cent, and there are thousands of calls per hour. The total cost is very high. Maybe the call granularity, one service call for each user request, is not optimal, especially because the service accepts batch calls containing up to 20 requests metadata for the price of a single call. So, for economical reasons, it becomes very useful to throttle the external service calls and to have each service instance wait until it has processed 20 user requests before sending all the metadata in a single batch call. By the way, this is the local data inside each instance, not of the whole Cloud Run service. Now we have a problem. What happens to the clandestine instance state when the instance is abruptly shut down? By default, the data is lost, and we violated our obligation to log every user action. Unless we have a way to execute some code just before the instance is terminated. Then we can use this information as an opportunity to call the external service with all our unsent data and not lose anything. This is exactly why Cloud Run now sends the seek-term signal before it terminates an instance, to give it a chance to gracefully perform any necessary cleanup. Here we will simulate exactly 197 requests to 3 customer services with a different granularity strategy and observe the result on the external service usage and invoice. What I call a customer here is a Cloud Run application. Before the test, we assume all counters are 0, the number of API calls for each customer and their monthly charges. Let's see. So if I refresh, yes, all the counters are 0, volume is the number of end-user requests reported, API calls to the external service, and the total price from the point of view of the external service. So I will now launch 197 requests to the Cloud Run service of customer 1, and I will inject the same load to customer 2, and the same, of course, to customer 3. Maybe some data is already arriving in the dashboard. Yes, it is. So the first customer makes an API call for each incoming end user action. Here we can see the total volume of end user requests reported is the same as the number of API calls. The second customer tries to make a batched API call every 20 user actions. So the volume reported here is a multiple of 20. Here 5 API calls for 100 end user requests reported. The third customer makes a batched API call every 20 user actions and catches the SIGTERM signal on instance termination. The problem with customer 1 is paying a very high price. The simulation here costs them €2. The problem with customer 2 is having some state kept captive inside Cloud Run instances and losing some data when an instance is terminated. So the volume 100 here might never reach 197. Customer 3 is solving this problem by making an extra batch call on shutdown if the instance is still holding unsent data. So at the end of the simulation, I will show you how it does it in a Go server. So this is a regular Go application for customer 3. It handles some handlers, etc. It does hold some state, for example, the number of unsent notification of end user request. And before starting the server, it registers to be notified for each SIGTERM signal, and it reacts by flushing its state. And by flushing, I mean making an external service batch call with any remaining data. Okay, so at the end of the simulation, the total cost for customer 3 should be around 15 cents. Okay, here it's 12 cents, which is way cheaper than the initial €2. As a conclusion, because we don't live in an ideal world where everything is free and performance doesn't matter, we sometimes have to wander away from the stateless dogma. The SIGTERM feature is what enables graceful instance termination. That's it for today. Thank you very much for watching.
Thanks, Valentin. This was great to learn about this new feature of Cloud Run, which is currently in beta. We'll see you in a bit for the Q&A section. A reminder to everybody who's watching this live that you can ask questions simply by scrolling down the page, and we'll get to these questions at the end of this section just in a few minutes.
So to close out this section on infrastructure and ops, we're going to hear from Katie, who will, she's implemented a repeatable deployment with Terraform on Google Cloud with a manually deployed service to Cloud Run as her starting point. Take it away.
In this demo, we're going to automate the provisioning of serverless infrastructure with Terraform. Here's a service I've created earlier. I've already built a container image based on this very simple web service. I have a very small Flask application that will print out hello and then world. I've created a Docker file to build the image, which I've already done. And I've documented for myself how I want to deploy this image. I can use gcloud run deploy, which as part of the Google Cloud documentation for deploying a new service is right there in the documentation, exactly what I need to run to deploy. However, I could have different deployment methods such as the console or Terraform. Terraform is an infrastructure as code system which allows you to declare exactly what you want your project to end up looking like. As part of the documentation, I can go in here and enter in the values that I want as part of this sample manifest. If I want a Hello World service deployed in US Central 1, my image that I prepared earlier is Hello World. I can copy this into a file called main.tf in my local file system. And what this will do is with the provider for my project, it will create a resource which is a Cloud Run service. It will use the image that I've prepared earlier and it will define a Google IAM policy that will allow all users to invoke my service. This is effectively the allow unauthenticated invocations or public service. As part of the documentation, if I've already installed Terraform, I can run terraform init, which will initialize Terraform within this current file system, downloading plugins as it needs to, and then I can run terraform apply. Terraform apply will go to the project that I've declared, check its current state compared to what state it has been told about, and have a list of differences that it will apply. In this case, since I have no services, it's going to create everything for me. It's going to create with the little plus. Once I've confirmed that that's exactly what I want to happen, I enter yes, and my service is created for me. Terraform allows you to declare exactly what you want in code and commit that code, which allows you to have all the bonuses of source control and rollbacks and timestamping and all that other nice stuff as your infrastructure. So if I refresh the console over here, I now have a Hello World service that says Hello World. Now this is a very simple service. Where Terraform really shines is where you start getting into complex infrastructure and non-trivial provisioning requirements. Here's a service I've prepared earlier. I have an application which uses Google Cloud Storage. It assumes that there's a bucket and it serves data out of that bucket. I have a very similar Docker file to before, and in order to deploy this service, I need to have a bucket already created. I need to upload images to that bucket. I need to build my container image, which I've already done, and I need to deploy that image. What I've already done is, as part of the documentation, there is a lovely little link here to the Google Cloud Platform Provider documentation as part of Terraform. This lists every single type of thing you can build in Google Cloud and how to declare it and talk about it in Terraform language, HCL code. So in here, if I look at cloud storages, I can create a bucket, I can create objects, I can create a whole bunch of different things. What I've done is I have a project variable here that I've declared, which I'm using throughout to have this all variable based on my project name. And I've got here an object, which as part of the documentation, I know that I can create a resource with a source in a bucket. This is in my local file system. I have a whole bunch of cats. It's very good. And I've already deployed this service using this manifest. If I was to perform a Terraform apply and I give it my project value, it will go through and work out based on what I've declared what the state of my service, my project is. And it's seen that there are no changes that need to be applied. Where this really shines is if you were to, say, accidentally delete your media bucket. I don't recommend you try this at home unless you have a complete manifest of how to reassert all the contents of your bucket, but I have. So if I run Terraform apply again, and I enter in my project name, Terraform will go out and it'll work out I've still got my service, I still have my IAM documentation, but I haven't got my bucket anymore. So it's asking me, hey, I want to create a bucket for you, and I'm going to put in some sample data. Is that cool? Why, yes, Terraform, that is cool. So if I give it a couple of seconds and refresh over here, it has recreated my bucket, and if I refresh my service, my one sample cat is back. Terraform can reassert your provisioning infrastructure for you, but it can't do things like create your container images or create your data. Terraform is very good at infrastructure provisioning. Continuous deployment, source control, and all that are better served by other tools. But hopefully you've seen today how you can use Terraform as part of your deployment mechanisms. Thank you for your time.
Thank you so much, both of you, for your demos, and thank you for joining us for Q&A. Alexei, do you want to ask our first Q&A question?
Absolutely. The first question reads as follows. Is there an API for every language to handle the SIG-term signal? And I guess this one is for Valentin.
Yes. Can you hear me, Alexi?
Yes.
Cool. So an API, yes, basically this part is not specific to Cloud Run. You can write your server in any language and deploy, wrap it in a container and deploy to Cloud Run. So depending on your programming language, in the standard library, the signal handling capabilities may be called shutdown hooks or Unix signals or capture callback, but yes, you can do it in any language.
Great. Our second question is about Terraform. What other Google services can be automated this way? And this one's for Katie.
That's me. If you look up the Google Terraform provider, it'll list all the different Google services that you can automate. So everything from App Engine, Cloud Build, Cloud DNS, Cloud SQL. If it has a resource that's being created in the provider, then you can automate it with Terraform.
Oh, great. So this question is actually for our Ops app. So I'll let you answer it, Alexi. So the question is, what is the expected cost of running the demo Ops app? Is there a way to properly shut down all the resources?
Right. So cost is always a concern, and rightly so in the cloud. So we should be able to control all of that. And in this case, the cost of running this specific CloudOps demo app can reach about $15 per day. $15 per day because you actually have a full cluster running and we're simulating load. So there's quite a few things happening. Of course, we would recommend that you use the $300 trial credits if you're a new user. That would cover quite a few days right there. I'll let you do the math. To shut everything down, make sure there are no costs involved. There is a sandbox CTL utility, and that will destroy everything and tear down all the resources automatically. So, and of course, all of this is an open source project hosted on GitHub. So you can see for yourself how all of this was built and provide feedback or improvement suggestions as well. So here's a question here, and that question is from Guillaume. Hello, Guillaume. Hi, Vincent. Might be Valentin in this case. Min instance equals 1 solves cold start from 0 to 1. Does it also solve the cold start from n to n+1?
Okay. Hello, Guillaume. Thank you for this question. So this does not solve the general problem of n to n+1 cold start. However, the higher you set the value for the parameter min instances and the fewer cold starts you will experience.
Yeah. So our last question for this section is for Katie. We hear that Terraform is the IAC tool du jour. I'm with a lot of French people. We'll use that term today. Will I have to switch to something else once its usage has faded in favor of something else?
This is contentious. So Terraform is an automation platform that helps you codify what already exists in the official Google Cloud APIs. Those APIs are used by Google Cloud, they're used by the Cloud Platform console itself, and they're not going away. The Terraform provider itself is open source, so you can jump in and fix things up, but Terraform or any tool running out of vogue is a bigger question. Serverless is only so new. Terraform is kind of cool right now, but it's a sort of a bigger philosophical question and not something that I was expecting to answer at this time of day. All technology is going to have ebbs and flows, I guess is the answer.
That's a fair answer.
Yeah. Thank you for answering it today.
All right, so with that, I think we've come to the end of this Q&A section. We will be in just a moment starting our third and last section, which is all about app development. See you in just a moment.
Welcome back, everyone. So we are now entering our third and final section of Next on Air EMEA Demo Derby, app development. And we have 5 demos to get you inspired to build apps.
First up is Mark with a demo showing us how to move your code from a local development environment to a test environment and eventually to production. Welcome, Bart. Welcome back, Mark. It's all yours.
Thanks, Alexei. Hello, everyone. If you're like me, you don't like changing your code when you have to move it from one environment to another. And I'd like to show you how I can take a simple app and move it from development to containerization to production in 3 simple steps. So we're going to do this at old school with the command line. I've got a really small app. It's the Python equivalent to Hello World, except that it's built for the web. So what you're looking at here is I'm using the Flask library, Python library, which sort of is an inversion of control library for making it easy to build web apps. And I've got a little bit of routing here. This is so that you can specify either the URL or a little suffix after the URL. Depending on what you specify there, it'll either say hello world if you don't specify anything, or hello whatever suffix you add to the end. And it's doing one little additional embellishment, which is it's generating a random number to style the background of the text with a random color, just for a little visual cuteness. So we'll run this app locally, like so, and not sure, oh, there we go. Wasn't sure why it was blanking there. And then we'll visit localhost :8080, which our app told us that was where we were listening on. And as you see, we get the expected hello world with a random colored background. Nothing terribly impressive. And as I also promised, I can add a suffix after the URL and it'll say hello Mark. So a very simple app, but it should serve as a nice example for our progression that we're going to do. Now, if you look at this app, it's got only one dependency, which is Flask, and that's fine. But let's imagine I give you my source code file and you run it and it doesn't work quite right because you have a different version of Flask. Yes, I can encode the version number in the requirement.txt file, but maybe I forget about an application or a dependency. Maybe I've got something installed in my environment and I forgot that I pip installed it a long time ago, and you don't have that, or you have a different version. So there's lots of pitfalls. I don't have to tell people about the problems with application packaging in 2020. But one nice way of solving this problem is to do what we call containerize the app. And I'm sure many of you know about this and have used it, but I'm going to use a tool called Docker to essentially bundle up the app with all its requirements into a sort of self-contained module, which will have everything you need to run the app with the confidence to know that all of the dependencies are included and there's going to be no surprises. So in order to do this, I need to have what's called a Docker file. And this can be thought of as a blueprint for how to build this module. It has a base image. So think of this as sort of a foundational layer in the container. I define a working directory. I add my 2 source files. One is the actual simple Python file. The other is the requirements.txt file. I run pip install to gather the requirements into the container. And then I tell Docker to arrange things so that when the container starts up, it should fire off this command that I just ran interactively, python hello.py. Now to do that, and so I don't sort of stumble around with commands, it's a little more involved than just saying python hello.py, but it's not that much more involved. I've got a script here to simplify it. Set-x is just a way to have the script echo the commands it's running. So that's more for me in debugging. Then I set this tag environment variable to be a unique identifier for my container. I do Docker build of the current directory. That's what the dot means. And I give it the tag to uniquely identify the result. And then I say Docker run. I give this -p argument to say map port 8080 on the host, that is my laptop, to port 8080 inside the container, because the port mappings are completely independent. So I'm just making sure that if I specify a port number in my browser to test this, the plumbing will kind of take it through to the same port number inside the container, and then I specify the ID of the container. So let's try running that. Ldeploy. It's doing the Docker build step. Should be pretty quick. Maybe I need Jeopardy music to play in the background here. There we go. Okay, sorry about the delay there. We see all the steps that were involved in the Docker build. And then we see that it was tagged, and we see the Docker run. And we can verify it's running by saying Docker PS. Let me bring this up a little bit. There is our running container. And now if we go back to the same site, when I reload the page, we see it's still working. Now you might be wondering, is that really working, or is that some artifact in the background? So what I'm going to do is stop the Docker process. I'll specify the container ID. Docker lets me just specify the first 3 characters of the container ID, which is convenient. Now, if I do a Docker PS, there's nothing running. And now if I reload the page, I get this site can't be reached. So I really was using the Docker container. But the great thing about it was everything you needed to run that app was inside that Docker container. So if I gave you that container image, we would both have the confidence that you're using the same bits that I'm using when I run this app. That's fine, but what if I wanted to deploy this container in the cloud and let other people just run the web app, just access the web app, and I wanted somebody to take care of all the administrative stuff for me? And that's where Google Cloud Run comes into play. This is a service where you can just essentially send us your container, send Google a container, and we will deploy it and take care of all of the administrative stuff. To illustrate this, I'm going to show an rdeploy script. So ldeploy was locally deploy in a Docker container. rdeploy is remotely deploy in the cloud. The logic here is very similar. It's doing the Docker build of the current directory with a tag. It does an additional step, which is Docker push. So that takes the resulting container image and pushes it up to the Google container registry. And then I run gcloud run deploy, and I pass it the app name. That's the service I want to have associated with my deployment. The image identifies the name of the container that I want to deploy. The rest of this is configuration stuff like the project, what region I want it to run in, etc. And the final argument is very important: allow unauthenticated. That means anybody can come and navigate to this site and run it. So let's run that, and we'll see how quick it is. It's doing the Docker build, and while we're letting that think, I'll just show you what the console page looks like for Cloud Run. I have all of the services that I've defined in a nice list. Tells me when it was last deployed. I can click down into, this is the one I'm playing with right now, MCO Hello Python. I can click into that, and let's see how it's going over here. So it finished the Docker build, finished the Docker push, and now you're getting to see how long it takes to actually deploy the revision. So right now it's doing the gcloud run deploy command, and it's giving me a little bit of a text-based summary of what's going on. I can do this on the console as well, and that's up here. If you say edit and deploy new revision, or I can even create a new revision up here where it says create service. But let's drill back down here and hopefully see if it's deployed. So it is deployed. That was done. Only took a few seconds to deploy a new service. It's getting 100% of the traffic, and it gives me a URL that I can click on. If I go to the console, I get the same URL. And one thing that's nice about it is this HTTPS. So I got automatic SSL encryption for free. Didn't even have to think about it. And if I click on that link, it shows me the now familiar Hello World app with the random background color. So that is all working nicely. A couple of things I also wanted to tell you about is you can set up continuous deployment. And in that case, you can push to a repo and it'll automatically pick up the changes and redeploy the service for you. You can manage, excuse me, custom domains. So just yesterday, I bought a domain called mco.test or mcotest.com. And a new feature in preview right now is you can actually search for and buy new domain names right within the Cloud Console here, which is super convenient. If you've done this before, you sort of have to ping pong back and forth between domain registrars and providers and the cloud. Now you can do it all in one interface. And at the result of that step is you can use your own private domain and it'll route you to the same Cloud Run service. One last thing I wanted to show you was the scaling. I'm going to run a test which runs 15 clients in parallel, each one doing 1,000 requests per second for 15 seconds. And we're going to see how it runs. And the thing to note about this is that the response time kind of pops up at the beginning, and then the service starts to realize it needs to scale the resources to keep up with the demand, which it does. And then the response time kind of smooths out apart from this little blip. And we get down to a nice, reasonable 67 milliseconds for the bulk of the test. So that just illustrates, and that's running on the exact same service I've been showing you, and that just illustrates how effectively it scales. So in summary, we went from, a local app to a containerized app to a production app, which included automatic support for SSL, scaling, versioning, and routing, and custom domain support. Really impressive set of capabilities. And if you go back to my first statement, how many lines of code did I have to change to make those transitions? 0. So I hope you enjoyed that demo, and you try and like Cloud Run as much as I do. Thank you.
Amazing. Thank you, Mark, for this very detailed step-by-step approach. I love how many things you get for free using Cloud Run nowadays. So just to remind you that you are able to ask questions to Mark and to every speaker in this section if you scroll down in the page that you're currently watching. And we'll get to those at the end of this section.
Great. So next we have Katie back. So this time she'll be showing us a BuildPack demo. What could you get how can you get all the benefits of containers without actually having to worry about learning the intricacies of writing Docker files? Take it away, Katie.
In this demo, I'm going to deploy a web service to Google Cloud Run without having to write a Docker file. Here's some code I've prepared earlier. This is written in Python, and as part of my own README, I've documented exactly what commands I need to run to get this website running locally. I need to create a virtual environment, initialize it, install a number of dependencies that I've specified in our requirements.txt file, and then I need to run Flask. Copying and pasting these commands locally, I can get this website running on my local machine in just a few seconds. And there we go. In order to get this service running on Google Cloud Run, I'm going to need to encode this website into a container. Now, normally I could do something like create a Docker file, which would do things like install the requirements.txt for me. However, requirements.txt and pip installing is extremely common. What we've done is at Google Cloud, we've created a whole bunch of build packs that, for common languages such as Python, Node.js, Java, and Go, will do a whole bunch of these fairly obvious things for you. All you need to do is specify what command you need to run to start your web service. As part of the buildpacks.io specification, I need to specify a proc file. Within my proc file, for a web service, I just need to tell it what command I need to run, which I can copy and paste directly from my documentation. As part of Google Cloud Run's container contract, I need to specify that for all IPs on this particular container, listening on port 8080, I want to run this particular command. That is the only file I need to add in order to get this deployed. From here, what I can do is I can install and run Pack on my local machine, or I can use the Google Cloud Build infrastructure to do it for me. In this case, I've already installed the Google Cloud CLI, and I want to run alpha build submit pack and specify that the image I want in the end is going to be within my project, and I'm going to call it my app. From here, Google Cloud Build is going to run pack, create the image, and then push it to the Google Container Registry. Since I'm using Python, and Python is one of the languages that has been encoded into BuildPack, what it can do is it can automatically detect what I'm doing and run these many basic commands for me. It's detected that I'm running Python and pip, and it's going to do all this for me. The isolation layer is already handled by the fact that it's in a container. Then it's going to install my requirements, and it's going to set my entry point as being that command that I ran. What that means is whenever this container is invoked, this is the command that's going to run on start, or the entry point. Pack will then finish up and push the container that it's built into the Google Container Registry. From there, I can get Cloud Run to deploy that container image. So with gcloud, I can run deploy a service called my app, and using the container that I just created on the managed Cloud Run platform, I can have it as a public service and it will deploy. Cloud Run doesn't care what made your container, as long as it's a container image listening on port 8080 when it starts up. And now I have my web service. This was all created just by adding that one proc file with the command that's custom to my particular application. If you want to find out more, you can check out the Google Cloud blog announcing Google Cloud Build Packs. Thank you for your time.
Thank you so much, Katie. That was really interesting to hear about how you can really speed this up, and all this container building expertise you no longer need to worry about.
It is now time for our next demo, and Guillaume will walk us through the exciting and newly released Cloud Workflows product, in this case applied to orchestrating microservices. So here's Guillaume.
Hello everyone, and welcome to this demo about Cloud Workflows. I'm Guillaume Laforge, I'm a cloud developer advocate, and you can follow me on Twitter at @glaforge. So Cloud Workflows, that's a brand new product that we launched a few weeks ago. The idea is to let you orchestrate and automate all sorts of API, HTTP-based API services. When you are actually splitting a big monolith into smaller microservices, it becomes harder to let them work together, to compose them together, and to actually follow and see how they behave properly together. Things like if a service failing, how to retry, etc. So the orchestration part can become more complicated and harder when you are developing tons of microservices. So Cloud Workflows is here to help you orchestrate all this, to automate complex processes, whether it's business processes or technical processes. And what's nice with Cloud Workflow as well is that it's a fully managed service. You don't need to set up any kind of infrastructure, and it scales automatically for you according to the number of incoming executions of your workflow that you have. And it's a pay-as-you-go pricing model, which is nice. So let's have a look at a first workflow. Let's start with the the classical hello world. So let me show you within the Cloud Console what a hello world looks like. So it's actually a YAML file. There's just one step here, the hello step, and you can return some value. So if I execute this, it's going to just return the value. Execution, it's going to create an execution. The input, there's nothing in input and output. Hello from Cloud Workflows. Workflows can be invoked from the gcloud command line, from the Cloud Console UI, but you can also invoke your workflows from, for example, a function. Here I have a function that is so it's a Node.js function that is using the Google Cloud /Workflows NPM module, and I'm going to create an execution for my hello workflow. Okay, so it creates an execution, and then I can query this execution to see if it was successful, because an execution can take a little while, so I can check later on that the execution has run properly. So here the second await call is checking the result of this execution, and then that's what I'm returning. So if I call this with testing, I click the test button, and then it should return again the same hello from Cloud Workflows value. All right, so that was our first example workflow. Let me show you something more interesting. Workflows, so they can output some value, they can return value, but they can also take arguments. Here I have a new workflow with just one step within the main workflow. But here notice the params key, which takes an argument, an args value. And this is actually some kind of object which has a first and last property. And I'm going to return an expression. Look at this dollar curly brace and then some concatenation of strings. That's an expression, so you can create expressions. Let me execute this. So the input value, you need a first name, Guillaume, and a last name, Laforge, and then I'm going to click the execute button and see what it's going to give. Oh yeah, it concatenated my strings. Hello, Guillaume Laforge. So as you can see, input, output values, that's working. Next, the next example I'd like to show you, it's something a little bit more complicated, and as I promised, you can chain and orchestrate all sorts of APIs together. So I have this example which is going to chain two cloud functions, but it could be a Cloud Run service, it could be an external API, it could be the Cloud Vision API to analyze some pictures, etc. So here in this third example, you have 3 steps in the workflow. Notice the steps are a little bit different. Here, the first one, get random number, is calling a cloud function which is returning numbers, random numbers from 0 to 99. So this function here, that's this one. It's returning a JSON document with one key number, and the value is basically a number between 0 and 99. And I'm going to store, it's something new here in this workflow as well. I'm going to store the value in this variable. It's a variable basically. Then I'm going to call another function. I'm going to call this cat poem function. It's a poem called The Cat from Charles Baudelaire, and I'm going to return a verse from that poem. And I'm going to use the random number for that. So let me show you this other function as well. So I've got the poem here that I'm splitting into individual verses in an array. And then I look at what's in the query string or in the body. I look for an nth parameter. And then I'm going to return the nth verse, modulo the number of verse of the poem, because I really want to have one verse, even if I've got a big number. And then I'm going to return that verse in the output. So let's see how I'm using that in the workflow. So I have this random number structure coming here. I retrieve the body of that JSON document, and I'm accessing the number key of the JSON document. And I pass this as the query of my second function. And I'm going to store the result of that function into another variable. And then the last step, well, I'm just going to output the body of this function, which is the verse I'm interested in. So here I'm going to chain those calls together. I'm going to execute this, and okay, I've got one example, one verse. I can execute it again. I'm going to get another random verse from this. Okay, so that's a more complex example of a workflow. Last but not least, I would like to show you as well something interesting beyond variables, etc. And calling HTTP based services and APIs. Here, I'd like to show you that you can also assign variables. So for example, I had my random number, but I was using random body number to go through the structure of the document. But I can store in this step, assignments, assign vars, I can assign the int value here in my number variable. And then I can do a conditional switch over that variable. So if the number is below 33, I'm going to the next step, which is low. If the number is below 66, I'm going to go to the medium step, and otherwise I'm going to go to the high step. So I've got the 3 low, medium, high steps, and I'm going to use again an expression, say, okay, that's pretty small number, an average number, a big number. And again, I'm going to use this dollar curly brace syntax for more complex expressions. So I can route the workflow through different steps using conditions, basically. So let me execute this. Execute button, and then, okay, 67, yeah, that's a big number. I can do a second execution, and this time, 65. Okay, that's an average number. As you can see, there's tons of things you can do with conditionals, steps, etc., and expressions. And there's more. If you need to do authorization and authentication to communicate with third-party services, you can take advantage of OpenID Connect or Auth2, or leverage service accounts and IAM policies. You can interact with any APIs internal. For example, you could push some message on PubSub. You could update a value in Firestore because there's a REST API for this, or any external third-party API that could be on-premise or in another cloud if you're in a hybrid cloud scenario. You can also modularize your workflows with sub-workflows to make things a little bit clearer. It's a bit like methods or procedures, if you will. You can handle HTTP status codes, things like, there's a 200, that's fine, but if there's a 4 or 3 or 5 or something error, you can catch these. You can also raise exceptions yourself and catch those exceptions. There's when something is failing and you want to retry, there's a retry policy, and you can customize this, the number of retries or the backup configuration. You can also create a sleep step if you want to wait a few seconds for something to happen. And otherwise, you can, within the expression support, you can assign and use arrays, dictionaries, etc. If you want to dive a little bit deeper, I encourage you to have a look at the Cloud Workflows documentation on cloudgoogle.com/workflows. There's a great video by Philip Knapik, the PM, the product manager for Cloud Workflows. It's a great introduction to Cloud Workflows. And last but not least, I would like also to point you at a hands-on code lab by my colleague Mete at Hamel, which is great to get your hands dirty and orchestrate several APIs together. I'm looking forward to see what you are building next with Cloud Workflows.
Hello, and thank you, Guillaume, for this first look at Cloud Workflows and the possibilities that it opens up. I can think of quite a few myself. A reminder that you can ask questions at any time by scrolling down, and we'll try to get to those by the end of this section.
I am really excited to see this next demo. It's by Mete. He will dive into an event-driven data processing pipeline to extract COVID-19 case numbers from a BigQuery data set. Then he'll show how to generate charts for specific countries, send daily email notifications with the data. So all of this is going to encompass Knative, Cloud Run, BigQuery, and SendGrid. Take it away, Mete.
Now, this demo that I want to show you, it's a BigQuery processing pipeline. And what I want to do is that, I'm based in London, and we started having lockdown in mid-March. We all started working from home. And at the time, COVID was a new thing. So I was checking the number of cases in London every day, at 4 or 5 p.m. I would check out and see what were the numbers for the day. So after like a week or two, I thought to myself, instead of me checking these cases by myself, why don't I build a pipeline that would check these numbers for me, and then it would send me an email every day at a certain time with the latest numbers, and maybe it will send me a chart as well. So I I basically wanted an easy way to see the numbers for every day without me having to check for it. So that's when I started building this pipeline. So the way I built this pipeline is kind of like this. First, I said to myself, okay, how can I get this data? Where can I get this data? And in Google Cloud, there's something called BigQuery. BigQuery is a data warehousing solution, and the good thing about BigQuery is that it comes with lots of public data sets. And one of those, not one, but a few of those data sets is related to COVID. So what I did is first I built a service called Query Runner. This is a Knative service that will go to BigQuery and it will ask BigQuery using the COVID data set, what are the number of cases for this country in the last month or so, right? So it will query that, it will get that data, and it will save it to a temporary table. You can create temporary tables in BigQuery, so I will ask to BigQuery and save it to a temporary table. So that was my service number one, but I wanted this service to be triggered on a schedule, so I used Google Cloud Scheduler to trigger that service once a day at 4 p.m. for United Kingdom, for example. Now, once I make this query and save it to a table, I send a custom event. So I reply back to broker and say, okay, I run a query. So I just reply back with a custom event that goes to another service called Chart Creator. It's a Python service that will read this table and it will create a chart from it using Matplotlib library, right? So it will read this table, create a chart, and it will save it to a Google Cloud Storage bucket. And then I set this bucket so that when an image is saved here, a chart is saved here, it will call another service called Notifier, which is another Python service that will use SendGrid to send me an email. And it will say, okay, there's a new chart created in the storage. Here's the link to go and take a look, right? So the good thing here is that it's event driven. So the scheduler triggers the event, and then that triggers the whole chain. But none of these services, they know each other. The query runner just runs the query, then sends a reply back to sends a message back to broker, and then that goes to Chart Creator. All it does is, it kind of just reads the table and creates the chart, so it doesn't know that there's a query runner. Similarly, Notifier, all it cares is that there's a new chart in the bucket, so it gets a notification of that. So the whole thing is loosely coupled, event-driven, and in the end, I get an email at the end of the day. So let's actually look at this in detail. So first, let me show you the code, not the code, but the configuration at least. And the code is on GitHub, by the way. So if you look at BigQuery, first what I need to do is I need to create scheduler sources. So in Knative, there's, as I mentioned, in Knative GCP project, there's different sources. So in this one, I'm saying I'm going to use Cloud Scheduler source, and it will be triggered every day at 4 p.m. and it will send a message to the broker with this data, and the data is United Kingdom. And my broker will pass this to my query runner, and query runner will get this United Kingdom data, and it will say, okay, I'll ask BigQuery what's the numbers for United Kingdom is. So that's my scheduler source. Then the storage source is my charts. Once I save my charts, after the chart creator saves the charts, it will send a message to the broker, and the broker will get the notification that there's a new chart in this bucket, right? So these are a couple of my sources. If you look at the query runner, I mean the code itself, we don't have time to go through it, but basically it gets the cloud event. So this is the event reader that I created. It gets the cloud event, then it extracts the country from it, then it runs a BigQuery job, and then once it does that, it sends a message back to the broker that I ran this job, and there's a new table. But the interesting thing is to look at the Knative service. So the Knative service is the query runner that just points to the query runner container, and the trigger, it triggers on filtering on job scheduler. So it only looks for Cloud Scheduler events. So only triggers on the Cloud Scheduler events, right? So that's Query Runner. Then after that, it goes to Chat Creator. And Chat Creator, we don't have to look at the Python code, but if you look at the trigger, the Chat Creator will only look at the query completed custom message, right? So this is a custom message that the Query Runner will emit, and then it will go to this Chat Creator. And then similarly, Notifier will only trigger on object finalize. So whenever there's a storage bucket update, it basically will emit this storage object finalize event, and this is what the notifier will get, right? So let's actually set this up and see if it works. So let me get out of here and go to eventing, processing pipelines, BigQuery. Now, I think I can get rid of this. Okay, so let's make this a little bit bigger. All right, so let's first create the scheduler source UK. So this creates the Cloud Scheduler source for UK. And then let's also create the storage source so that when we say the charts, we get those events as well. And then we will get into Query Runner, and then we'll create the Knative service and then the Knative trigger for that. And then let's do the same for Chart Creator. And then let's do the same for Notifier. All right. So if everything goes well, we can look at our services. So you can see that we have 3 services that's been created. And then we can look at the triggers that's been created. And the triggers, they are being initialized. They will talk to the default broker. And I already have a broker injected into my namespace. So the default broker is there. And let's also look at Cloud Scheduler source. So this is the thing that will trigger the events. And then Cloud Storage source is the thing that will trigger storage events. So everything seems to be set up. Now we can wait till 4 p.m. for it to be triggered, but we can also manually trigger this event. So if I do gcloud scheduler jobs list, we can see that there's a job that's been created that will trigger at 4 p.m. But let's actually trigger this ourselves. So if I do jobs run and then pass in the ID, this should trigger the job now. And then now the whole event chain is being initialized. So if everything goes well, this will go to the Query Runner. Query Runner will actually run the query. And if you actually look at the logs, you can see that we have the services running. So let's just take a look at the logs of Query Runner. Oh, sorry. Yeah, the Query Runner is actually terminating because they scaled down, right? So if I look at pods again, you can see that they scaled down. So I couldn't see the logs, but I think the whole thing ran. So if I look at my email, you can see that I got an email, a new chart from BigQuery Pipeline, and if I open it, I have a link to a chart. A new chart is available. Let's just take a look. You can see that I can see the COVID cases in United Kingdom. That I get the chart, from the beginning of March till today. So that's it. Hopefully this was useful to you. My Knative tutorial on GitHub, it has many more samples than I showed you today. Hopefully the samples that I showed you, it was useful and you have an idea on how Knative works. Also, as I mentioned, Knative, if you want to run Knative on Google Cloud, you probably want to use Cloud Run. And I also have a Cloud Run tutorial on GitHub for that as well. So feel free to check it out. Thanks for listening. And if you have any questions, feel free to reach out to me on Twitter. I'll be happy to answer. Thanks very much.
Thank you, Mete. That was a really great deep dive on a topical issue. So definitely stay tuned for the live Q&A, but feel free to use Twitter to send over your questions as well.
So, and now, as our final demo for this Next on Air EMEA Demo Derby, here is Valentin once again. Back this time showing us how Cloud Run is pushing the boundaries of serverless. Over to you.
Hi, my name is Valentin Deleplace. I'm a developer advocate for Google Cloud. Today I'd like to show how to stream an HTTP response in Cloud Run and why we may want to do this. This is a straight flush in Poker. I'm very sorry, but my presentation is not about Poker. In Google Cloud, all serverless services use to fully buffer the request and the response, making it impossible to stream data to the client. Until now. I will demonstrate one such traditional endpoint. This is the URL of a service deployed to Cloud Run, which performs 3 computations and returns the 3 results to the client. Let's send a request to this service using curl to the endpoint noStream. This is slow because each processing takes time server-side, and we get all the results at the end, processing 1 complete, processing 2, processing 3, when they have all completed after 6 seconds. Cloud Run now supports flushing partial response before the request processing is complete. I will show the code in VS Code. So this is how we do it in Go. First, we detect that we have a flushable response writer, and we call the method flush. So we flush after the first processing, and we flush again after the second processing. Let's try this by sending a request to this alternative endpoint. Yeah, it works. Now we get the partial results as soon as they are computed, and the total time is still above 6 seconds as expected. I have a mobile app designed to let me share a photo with the computer by scanning a QR code. The role of the QR code is for the computer to advertise a generated virtual address where the mobile can send the data via a broker server. So technically, the file is transferred via the internet, and the cloud server sits between the mobile source and the target computer. The mobile side is active. I need to install a specific app to add a new option in the Media Share app list, initiate a QR code, and upload the data to the backend. On the other side, the computer is supposed to display a QR code and passively listen to some kind of channel and receive an event with incoming data. I would greatly prefer to use a command line terminal for this and not have to install any additional software. Let's achieve this in a single HTTP request using curl. Curl is already installed by default on most Linux and Mac machines. The blue arrows here are a single HTTP request, a partial response containing an ASCII art QR code, and a response body containing the picture data. I know this whole workflow is kind of unusual, but don't worry too much about it for now. Let's do a live demo. I have a mobile phone, here it is. Let's see if I can display the screen. Yep. This is the URL of my service deployed to Cloud Run. When I send a request to this endpoint, I specify the flag -v to display the headers, because the backend will generate a QR code and write it in ASCII art inside the response headers. Then I ignore the first byte of the response body. That's a small quirk in my workflow. Then I redirect the response body to a new file X, and I open the file X. Let's see. No, that's not good. What did I do? Yes, I forgot the endpoint. Sorry. Okay, here it is a QR code that I will try to scan with my app. Yay, it works, and we now have this nice hedgehog on the computer. Cool! This use case would not have been possible at all without flushing, because the computer needs to have the QR code data before the mobile dispatches the file, which happens before the server knows what data to send in the response body. My example was written in Go, but of course you may flush an HTTP response in any language you're using in Cloud Run. There are many use cases to these new server-side streaming capabilities, for example, streaming large responses with chunk transfer encoding, or streaming a gRPC response. That's it for today. Thank you very much for listening.
Hey, thank you, Valentin. That was certainly an entertaining way to use QR codes and Cloud Run.
Yes, very cute, very adorable. Thank you so much. With that, it is now time for another Q&A session with the presenters from this section. So we will be right back with Mark, Katie, Guillaume, Mette, and Valentin. So let's get started with that Q&A.
Yes, as a reminder, you can still ask questions at this time by scrolling down. We'll try to answer these maybe now, or at least in with a written answer if we don't get to those. So welcome, Katie. Welcome, Mark, Guillaume, Valentin, and thank you all for your awesome demos and for joining us.
So let's get started with our first question. So our first question is from Radu. Thank you for typing it out for us. So build packs, what languages are covered? This is for you, Katie.
Right, so build packs, you can build anything in it. The build pack languages that are covered by the Google Cloud build packs are Go, Node, Python, Java, and .NET Core.
Excellent. So our next question comes from Tomer. Batch operations with cloud workflows, is it applicable, I guess? And this one's for Guillaume.
Yeah, so you can totally do batch operations. So the thing is, so a batch operation could be launched or triggered by the workflow itself, or perhaps scheduled with Cloud Scheduler. The thing is that with the conditionals, well, first of all, the batch operation usually has some kind of side effect, like returning a result or updating some value somewhere, etc. Within the workflow, thanks to the conditionals, I didn't mention it, but there's a sleep operation. So you can sleep for example, 1 minute and check, thanks to the conditionals, okay, is the result there? Is the result there every minute? And then you return the value once the result is available. So yeah, it's totally possible to do batch operations, or monitor or handle batch operations and track their results.
Okay, great. Thank you, Guillaume. Our next question also comes from Radu. It's actually there are a few. Let me read this out, and I think Mark will be here to answer this. Must rdeploy application be installed, or is it part of Docker? Would gcloud service account be already on the machine, on the local machine, where the rdeploy script is? And what are the needs or requirements into GCP for the rdeploy to do his thing? So Mark, this is for you, I guess.
Yeah, so if I try to generalize this question a little bit, I'm going to take a step back and just emphasize that there are always 3 ways to interact with the Google Cloud: the command line, the console/web user interface, and an API. So there's multiple ways you can sort of do what I did in that demonstration. But in the real world, I chose to use the command line, but in order to show you some of the mechanics of what's going on. But in the real world, you would use some probably more user-friendly and more sophisticated approaches, like you would use continuous integration, continuous deployment, to figure out that a repo had been changed, and to automatically build the container and to automatically deploy the container. And a lot of that's built right into Cloud Run. So that's a really good way to go. One thing I didn't mention is we have something called Cloud Code, which integrates some of these capabilities right into some of the popular IDE tools like VS Code and IntelliJ. So for the developer part of my little spiel, I would probably be using something like VS Code with the Cloud Code plugin. For the deployment, I would use a CI/CD pipeline. And to go to the question about the commands themselves, the ldeploy and the rdeploy, those were just little helpers, shell scripts that I wrote. And they were using gcloud for some of the heavy lifting. So I did have that indeed installed on my local machine.
Great answer. So our next question is for Mete. So if I deploy an app with events on Cloud Run, how much work is it to migrate it to a Knative install?
So if I understand the question correctly, if you have your service running in Google Cloud, basically, how can you take and move to some other place? Well, Knative, it's an open source project. It runs everywhere you have Kubernetes. So you don't really need to change anything about your service to move it. It's just a regular containerized service that uses probably the Cloud Event SDK to read the events, and then it can emit other Cloud events. So yeah, I mean, it's basically just taking the container and just running it anywhere you want, really. So there's nothing special about the code and where it runs. What is special is that how do you connect those services? So what Knative Eventing does is that it gives you these building blocks to connect these services in an easier way. So if you move to some other place, maybe the connection becomes a little bit more complicated than Google Cloud. But in terms of the code itself, I think that can run anywhere.
Great, thank you, Mete. Here's another question, I think, for Guillaume. Cloud workflows seem pretty quick from your demo, but can they not become a bottleneck or even a single point of failure? And how do you monitor them?
Yeah, so that's a great point. So actually, Cloud Workflows is really a fully managed solution offered by GCP, and all the scaling, etc., is totally is handled by GCP. So it scales automatically, transparently, without a problem. And there's also no cold start, so it starts right away when you ask for an execution of a workflow. It starts right away. For the monitoring aspect, so from within the Cloud Console UI, of course, you can watch the execution as they go through. You can also use the gcloud command line. You can do gcloud workflows execution. I forget the exact command. You can check that. You can even use client libraries to call with whichever language that you prefer to call the REST API for Cloud Workflows to check what's the current status. And or actually even in one of the demos where I was invoking the workflow from Cloud Function, I was also using the client library from Node.js to actually check the status of the executions. That was the second call. And last but not least, there's also the Google Cloud Logging as well, if you want to see what's going on. So yeah, that's that.
Thank you, Guillaume. I think with that, we've come to the end of this Q&A session on one side, but also to the end of our event.
Yeah, thank you everyone for joining us today for Demo Dear Me here at Next on Air EMEA. So with that, we would like to thank all of you for joining us. We hope this time was well spent for you, and we hope that you're inspired to build something in any one of these fields that we touched on today.
Thank you to all of our demoers. This was truly a demo fest. Maybe that's a new name we should use. Thank you, Anu, for hosting this with me.
Thank you for having me.
Goodbye, everyone, and stay safe.